until this point in this unit, we've been talking about intramolecular forces. Now, intramolecular forces are forces of attraction within a molecule. So they are within a molecule. Now, there are two different types of intramolecular forces that we have considered. First, we considered covalent bonding. Electrons are shared. Now, in a covalent bond, you can either have a bond that is polar, meaning that the electrons are not shared equally, or the covalent bond can be nonpolar, meaning they are being shared equally. The second type of intramolecular force that you can have is an ionic bond, in which electrons aren't shared anymore. They're actually donated from one atom to another. Now, in this lesson, what we're going to consider is not intramolecular forces, but instead intermolecular forces. Now, intermolecular forces are not forces within a molecule, but they are forces between different molecules. So, between molecules. Now, there are three different types of intermolecular forces. There are dipole-dipole, hydrogen bonds, and dispersion forces. So I'm going to go through and explain each of them. For dipole-dipole, for this first one, if you notice, this attraction is between two different molecules. You have HCl and another HCl. Now, if you'll remember from the last lesson, we discussed the fact that chlorine, because it is more electronegative, it will be partially negative, while the charge of hydrogen will be partially positive. Again, partial positive, partial negative, because of differences in electronegativities. Now, this dipole that exists is permanent. It always exists in this fashion. So, if you remember the fact that positives attract negatives, there's an attraction between chlorine and hydrogen because chlorine is partially negative charged and hydrogen is partially positive charged. This attraction is called a dipole-dipole attraction because you have these two different dipoles, and as a result, they are attracted to each other. So that is the first type of intermolecular forces. Molecules can be attracted to one another because of their permanent dipoles that exist. So that's the first one. The second type of intermolecular force is hydrogen bonding. Now, hydrogen bonding is a type of dipole-dipole attraction. However, it is very specific. It is a very specific type of dipole-dipole attraction. So if you'll notice, just to show you how it's dipole-dipole, if you have, let's say, NH3, hydrogen is partially positively charged and nitrogen is partially negatively charged. This attraction is not just a dipole-dipole attraction, it is a hydrogen bond. Again, here, partial positive, partial negative, partial positive. But if you notice, there are only three examples in which hydrogen bonding can exist. Between hydrogen and nitrogen, between hydrogen and oxygen, and between hydrogen and fluorine, because hydrogen bonding is fun, just to help you remember. Now, why are these considered a different type of intermolecular force compared with dipole-dipole? Well, the reason why, if you look at the position of hydrogen on the periodic table and the position of nitrogen, oxygen, and fluorine, they are so far apart that their difference in electronegativity is extremely large. Therefore, because this is so partially negatively charged, because it's basically almost stealing the electrons from its hydrogen, and this one is almost losing its electrons to nitrogen, this partial positive and this partial negative is much stronger than this partial negative and this partial positive. So therefore, because this is a much greater partial positive charge and this is a much greater partial negative charge when compared with other dipole-dipole examples, hydrogen bonding is extremely strong, and therefore we distinguish it between regular dipole-dipole attractions. All right, so those are the first two. The third one is a little bit more complex, but just for you to know, dispersion forces exist within, or between every type of molecule. So while, for example, NH3 has hydrogen bonding, it also has dispersion forces all the time. Okay? While HCl has dipole-dipole attractions, it also all the time has dispersion forces. So I'm going to explain dispersion forces really quickly. I'm going to kind of juxtapose this diagram right here, and I'm going to give you an example. Let's say, for example, I've got two helium atoms. And so helium, two helium atoms, helium has 2 electrons in it. So I'm going to draw 2 electrons. Now those electrons can be anywhere at any time. Okay, so I'm going to draw them on opposite sides right now. In one instance, however, if the electrons are here, it is just as likely that those 2 electrons could end up on the same side. So if I were to redraw this, those electrons, rather than being on either side, could end up being on the same side. Now, since these electrons are on this side, electrons will repel other electrons. So these electrons are going to repel this electron, forcing it to the other side, because negatives and negatives repel. Therefore, these 2 helium atoms will look like this instead. This is just in one instance. It happens that they line up, so they force the electrons of the other helium atom over to the other side. Now, if we consider just this one instance, if we consider charges, since the electrons are on this side of the atom, this atom would have a partially negative charge. Since the electrons were pushed from this side would have a partial positive charge. Automatically in your head, when you're seeing partial negative, partial positive, you should be thinking dipole. And there is a dipole right here. There's an attraction between the negative charge here and the positive charge here. The difference in charges is that dipole. So you've got an attraction, but interestingly, it looks very similar to the dipole-dipole attraction, except this dipole is permanent. It always exists like this. While for dispersion forces, it's just in one instance. So this dipole right here that was created is temporary. So you can see temporary right there. So it's a temporary dipole. So if you think about strength of these 3 different intermolecular forces, since this dipole does not exist all the time, this is going to be your weakest force. So this is your weakest form of attraction. Now remember, all molecules are attracted to other molecules through dispersion forces. They're attracted to each other ever so slightly, maybe not, it's not a strong attraction at all, but every single molecule or atom has the potential to have this instantaneous, this temporary dipole, and therefore the attraction between the partial negative and the partial positive. If you look for dipole versus hydrogen bonding, these have permanent dipoles, but this one, the dipole-dipole, isn't quite as strong as hydrogen. So hydrogen is the strongest, and the reason why, remember, is the difference in electronegativities between hydrogen and nitrogen, hydrogen and oxygen, and fluorine and hydrogen is the strongest.